Ladies and gentlemen, boys and girls, welcome back to another video. It's your boy. My camera's not working. You can't see my face, but does that really matter? You can't see my baby, though. I'm holding her. I bet you. Okay, so here we've got exam 3. This is all going to be optimization. This here is going to be practice exam because it opens what next? I don't know. It opens sometime. All right, let's get at it. So if the first derivative of a function is negative, and maybe I might as well hit up the if the first derivative of a function is negative, the function is concave down. We're saying the first derivative is negative. That means that it's. If you ever have a question like this, you're always going to be thinking of counterexamples, right? So if it ever, true, false, and it's like a statement in general about, general functions, you're going to be looking for counterexamples. If you can't find a counterexample, that's when you think maybe it is true. Let's see. But here, can you think of a counterexample? Guys, not concave up or down. Okay, I mean, maybe it depends on the way that you're defining concave. Concave up means greater than or equal. Then, like, I suppose, then it is concave. But if we're saying just strictly greater, then it's maybe consider a function. This guy here, first derivative is negative. The function is concave down. We notice here that at this point, because you can, how you draw your little u, this guy is concave up at this, but the derivative here is. Okay, so this guy is going to be false. Global max on an interval must be a local max of the function. We're saying that a global max on an interval has to be a. Once again, go ahead and get a counterexample. Think of a function, straight line here. Make your counterexamples very simple. Here's our interval a. So where are the global maxes and got a global min? So if this statement were true here, must be a local. Well, then we expect if it's a local max, then and when we say local max, globally local, it's just going to be like a critical point. Are these critical points? No, of course not, right? Because we not only do we have to check critical points, we also have to check our boundaries. But then the boundaries don't actually mean. The only reason this guy is special is it's the most on the right. That actually, this doesn't actually mean not look. Okay, the best linear approximation of 1 over 1.01 near x, one will give an underestimate of. Okay, so when you see these underestimate, overestimate questions, there's a couple ways. You can do is you can draw it first. So we could just get in here. We could get in here and draw. What function would you use? Well, it's 1 over 1.01. The weird number is where your x is. Here what we would do is we would draw 1 over. Drawing 1 over x, and like this one doesn't really matter. Okay, so we've got 1.01, 1, this guy, 1. Okay, so it's going to be a little bit to the right. Now go ahead and take a supporting tangent. And it's going to be like this. You notice that it's going to be under function. And that is all that matters. Problem for functions that are they're called convex, right? So convex function, like this function, the function is always going to, and convex just means that it's concave. Concave is, it doesn't matter for concave up functions. Actually the way that like in more like different types of math, you're actually going more generally not with second derivatives, but combination. It doesn't really matter. But anywho, a big point of these functions is that if you are concave up, any supporting tangent line will touch from the bottom, right? So if I were to take a function like this guy here, this supporting tangent line is going to touch from the bottom. If I take a concave function here, this supporting tangent touch from the, okay? So this means that if you follow along, now you could do all this right and still get the wrong, because you're thinking, okay, what is overestimate? If you follow along the tangent, this L is going to L, where blue is actually, we notice that green is below blue. A local max of f on the interval must also be a global max. Okay, so take an interval. Go ahead and right. So here we're going to be looking local max, also global max, and you're like, oh man, we're straight, right? But this is of course not true. Don't even think about just functions that you can write out the equation, but you can also think about just functions. This is like a quartic, something x to, right? And here you notice that clearly local max. Oh, okay. Actually, we'll do something. So this is a local max, but the global max is here. But the local max is on the left. Global. So, and then the same thing with min. Theoretically the same. Okay, a local interval must also be a global. False. The limit of this guy here, how do we evaluate? I'm going to be super honest. A little odd. It's in this. Haven't really. My dog. So we've got limit of. Oh, let me write it all down. Boop. If anybody's know how to do that, you press the window key, the shift key, S, all at the same. Okay, so here we're going. Okay, let's see. Got this guy here. So whenever you're taking limits, the same thing. You say, oh, x cubed plus something divided by like x squared plus. You're like, oh, this has to be infinity. How do you know it's infinity? Oftentimes skipped and it makes because really the way that you do this, the limit of x squared. So the limit of x squared divided by what is the biggest? Normally when you're doing highest x, really the 4x grows a lot bigger. X squared over e plus e to the 4x divided by 2x over minus e to x. And the reason that we're allowed to do this is because we're dividing by e to. Okay. Now that we've got this, let's simplify. This is going to be 1 plus x squared over divided by, let's say, negative plus 2x over this is okay. What is the limit here? As you approach infinity, we're going to have this. As we approach infinity, we're going to be having this is going to be x squared over e to the 4x. What's the limit? It's going to divide by, what's the limit of the like as it's going, the limit is basically, this is e to the negative 4x. All these are going to be 0 plus, but we have this negative sign. Negative is super important. This means that you're dividing 1 by 0, but there is this negative sign front on the only negative infinity. Okay. Let's absolutely. And another way that you could look at this is e to the 4 divided by negative e. This is all that's going to matter. Negative, which e to the x is going to infinity. So determine the absolute minimum of this guy here on the function. So what do we have to do? Of course, we know that we're going to have to check our critical points and check our boundaries. Right? We know this. Go ahead and this. Let's go ahead and do this. So we're going to paste the new problem. Okay, first step, step 1. Going to be take derivative and find critical points. Okay, so take derivative. So equals what? The derivative of 1 is 0. The derivative of 80x cubed x squared plus 2. And set this guy, so and this guy is going to have here, and so let's factor a little. We got an x squared negative 10 squared plus 20. Oh, 240. Okay, so this is what we have now. So we know that x equals 0. So now you solve. So x equals 0 will work. What else will work? Take out it. We can factor out a 10. Third times plus. Okay, so now we factor this. This guy here is. We factor it, and we're going to end up getting 6 and 4. Plus 6 minus 4. Tripping. Plus 6 minus 4. This would be negative 2. Wait, okay, so what we can do here, right? You can pull out a negative here and then positive, negative, right? So we have to multiply to negative 24 and negative 6 and positive 4. Negative 6 and positive. This guy is going to be x minus 6 and right. That checks out. Okay. So now that we've got that, we're going to say x equals 6, 0, 6, or -4. And then step 3 is going to be like check your boundary. So, and we also have 0 as, and that comes from where we get this. Hey, perfect. All right, we're in business. So we've got our points that we need to check, and now we just check them, right? So 3 is just going to be, step 3 is just going to be, right? So step 3, f of 0 equals f of 6 equals f of 4 equals f of 0. We're already checking, right? Because we already had an f of 7 equals. And then the max, so these guys are all going to be something, is the biggest of heat. N is, I'm not actually going to plug them in because you guys can do that, and yeah, the min should be like the -4, and the max. Oh no. Min should be the 7, and the max should be -4. I don't know. Check it. You can check. Okay, so let's see what we got going on. That's going to be problem done. I would check this to actually get the answer. And then now we're done. We can. Okay, and we're taking an antiderivative here. Yeah, we know how to. So all we say here is what is the. Well, let's copy and paste briefly. Have this guy right here. And we can say, okay, what is the antiderivative of so let's split it up because we've actually got a little bit of work. So the antiderivative x dx, and then these ones we can all do without like it. Plus the integral of -5 over x plus x dx, right? Okay, so what's the, bless you, what's the derivative of, bless you, what's the derivative of secant squared? Or sorry, what's the derivative, what gives you secant squared in a derivative, right? The idea is we have so and we should, well, I mean that's how you get it, right? So what is the antiderivative of secant squared? We know secant squared. Okay, so here we got to do a little bit of a use of x and dx. You don't have to do this once you start getting more comfortable with just these subs where it's just like a times x. But if it was like secant squared of x squared, you definitely need. Okay, so now we say that this guy is going the integral of 3 times 3 secant squared u x. And now this guy, the 3 and the dx make du, so this is going to be the integral of squared u. Okay. And then now we're going to have plus 5 over plus. Because now we can do all these. So what's the antiderivative of secant squared? We know it's going to be tangent. So this is 3 tangent u. Now we still have to plug back in what u is. Plus, let's differentiate this guy. What's the antiderivative of x to the 1? So we've got 5x to Sorry, no. Okay, don't do that because you're gonna be dividing by 0. What is the antiderivative of x? It's gonna be ln. My bad. Okay, so this is gonna be -5 ln x plus the antiderivative of x to the 25th. Well, it's gonna 20 x to the 26th divided by 20. And what's the antiderivative of e? You're gonna be like, oh, it's e, isn't it? All right, because the derivative of e is e. No. E is the number. E is like 2 points. This is gonna be just minus e. Not e to the x. E is just a number. Minus ex. And then our final step is just going to be replacing this guy. Don't leave u. E tan. What is the what is u? What is u here? It said that it was. So this is just going to be e tangent x plus. And then is this correct? If we were in like I would say that this is correct, right? And everybody would say yes, and then I'd say no, it's not, because you have to have plus c, right? If you had like this whole thing plus 4, well, the derivative would still. So plus c is very important. And this would actually be okay. Alrighty, I'm not going to write that, but that's how I have it. Okay, determine the intervals of concavity for the unknown function of. So what we notice here, and if it was ever like if you had a question like on a graph like this, just it doesn't have to be back because we don't really know exactly where the concav. The point that I make. Okay. Point that I'm making here is we know that it's concave down here, but at some point in here it changes because now concave. And so if you were on a test, you'd say probably, okay, well, like it's probably going to be negative 0.5 to 0. Like this is kind of where it looks like an inflection point, but you don't know that. Like if you don't have the function, it really could be 0.7 or something. Like we're not quite 100% sure where the concavity change. But that's a good guess. I would just say that the blue here is going to be concave up, and then the purple here, negative infinity, negative 0. Okay, critical numbers. Here next. E. All right. Let's get at it. I mean, you just say f prime, right? 0 is what we want. F prime of x. And what is f prime of x? 30x worth plus 33. 2 x cubed minus 90x squared, and then plus 100. Well, the 100 goes right. Okay, so we can factor out now. Let's factor out a 3x squared. So we have is probably the best we can. Yeah, so 3x squared times we have x squared, and notice that we can just factor the 3. 6. So that's gonna be 11. So what we can say is x squared, 10x squared. 10x squared plus 44x minus 30. Okay. So now this is what we have, and we just have to factor it, and then so how do we factor this guy? I mean, like, you'd hope that you wouldn't have to use quadratic formula. Oh, this is this should be. There's nothing else that we can factor, right? And we can factor a 2. Is that really gonna be? It's not gonna be helpful because I really don't want to have to deal. I'd probably just do quadratic formula. Maybe there's a way to factor it. I assume there probably is. But no, let's do quadratic formula because this is actually an important point. So if we do quadratic formula, right? So for this guy, x equals negative b plus or minus. We're gonna say root. Oh my goodness. Okay. So we've got negative b plus or minus the root of b squared. B squared minus 4ac. Well, what is ac? So negative. Okay, maybe 4a divided by a, which would be just right. Okay. So if you said as your final answer, this guy, comma, 0, right? And the 0 that you get here, this said comma 0. This would be a correct answer. Because I don't care if you simplify and do 44 squared plus what would be 1200. I'd, take what a square root of that is. What really matters here is that all we've done. So this here would be a complete. On the other question, like you could have done the same. Question 6. You could have done the same thing here when you're solving for your. Now here it's saying determine the absolute. You actually have to plug in. If you did quadratic formula, you're gonna have to plug in that quadratic formula. So I would recommend try your hardest to factor. Right, there probably will be a way to factor it. I'm doubtfully gonna. If you want to do quadratic formula, but if it's just saying find the critical, I do not need. Okie dokie. There's 6 minutes left before, and then we'll. Okay. Okie dokie. We read this problem. We need a constraint function and optimizing for. Bless you. Objective function. Okay, so objective function is it's your objective, right? It's what you want to do, and then your constraint is going to have to obey. So objective function, we want to build a box whose base length is times the base, and the box. Determine the that will minimize the cost, right? So box that will. So we're minimizing cost. What is cost here? Well, a box, right? The volume cost of it is going. Well, the materials for the sides are going to be $3 per inch. Cost of the top and bottom is going to be per inch. So what is the so we've got base length, base width, and base. So we're going to say height. The cost is going to be. How do we figure out what our cost is? Well, we have 6 faces of our, and so one of the going to be length times O is length times width. Other face is going to be height, and the other face is right. Got our box here. Right. We're going to have this guy here would be width times height. This guy here. But you notice we have two of them, right? There's also one on the bottom and there's one on this. So really all of these numbers, this is what we are trying. Now we're not, now you're thinking, oh, we're not trying to maximize, we're trying to minimize it. But you can always just take your critical. So this 2LW plus 2LH plus W is. Now, what is your constraint? Your constraint, I should, maybe I should have. So O, be this guy, and then C is going to be your constraint, and maybe this is this could be a little. Make sure you don't think that this is cost, right? It doesn't matter. What is our constraint? Maybe. What is constraint? Well, we know that the base length 6 and the box will enclose. So length times the length is going to be times the, and the box will enclose 20 cubic inches. That length, width, height, right? So this is step one. Always step one is get your function. Step two is going to be make O a function of just one, right? Variable. How do we make it a function of just one variable? What we're going to do is we're going to say that L is 6W. Okay. So now we have, so using, and I'm going to call, so we can keep track of our, so by star, we know that L is 6W, so double star. L this is going to be L was 6 times W times 8. In other words, this means that H is going to be 20 divided by. So L is 6W. W is just W itself. H is 20 over 6. Now we can get down to business. Step 3 is going to be plugging in. How do we plug in? Well, we're going to say that we have 2 LWs times O is going to be times L times W plus times L times H. And then we have 2HW. W. Okay, now this is all just W's, and you. So maybe we simplify a little bit. 120. We'll actually word that. Here we would be left. And then we have plus, we've got so we're going to have 40 over 6. Okay, so this guy here is going to be this, and now number 4 is, and that's just going to be want time to prime. It's going to be plus minus 40 minus, right? Okay, so what can we do now? How do we make um I don't think um we are fine. No worries. Okay, so now what we do here is we can multiply everything by w squared because we want the 0. So we still want 0 equals multiply everything by w. I don't know how to solve a inverse quadratic like this is, but we know how to solve a cubic. Multiply everything by w squared on both sides. So w squared times still going to be, this is still going to be 0. And then we've got 24w minus 40 minus over 3. And now we can go ahead and solve this guy for 0. Say that w is going to be, we're going to add over, maybe let's see, add over 40, divide by the 24, that's all, then take the cube. We don't have to do plus or minus. Remember, cube roots are actually just one function, one number. It's not going to square root, it's plus or minus. Here, the cube root is just going to be a number, and this guy here would have to be. If you ever have one critical point, it can only be your, because oh, they have worked out. They can only be one minimizer because you can make this infinite expensive. The way that you would do that is by like the top super big, and oh no, I did this all wrong. It's they're not equally priced. It's in 50. Shoot, man, my bad. Okay, so this is how you would do it if this was $1 per, and this was okay, the actual way that you should, okay, make sure you read the whole problem, right? This would be your answer otherwise. What we should actually do, we know that top, which is length times, going to be 15. We would add in a 15. And the other ones are 3. Okay, so if you go through, carry everything out, make your function this. When you plug in now, instead of this, same deal. And then video here. Now let's go ahead and make our real. This means that W 40 times 3 is 120. So 120 plus 20. And we're going to divide by 4. and then we take it. This is actually. Does this tell you how much it'll cost? Oh, it does not. Right? This tells you only what W is. So now to find the cost, didn't ask. The minimal cost, which I like this. So if this this is actually a really good problem for you guys know how to. Minimal cost would be it would be plug in and really you'd probably get your plug in. All right. If you have any questions, email me. I hope that you all have a good time all on the JTron.